Welcome to Engineering Drawing with SolidWorks. I am John Fielke, and in this presentation I'd like to cover the topic of linear tolerancing. At the end of this presentation, I would like students to be able to explain the difference between a bilateral, a symmetric and a unilateral tolerance, and be able to calculate and specify the limits of size for internal and externally assembled components. So tolerances, why do we need them? Well, tolerances are very important because it's impossible to make a component to an exact size. So we just can't add a number, say 10 millimeters. They'll say, well, how close do you want to be to 10 millimeters? Is it 9.5 good enough? Is 10.8 okay? Is 12 close enough to the 10 millimeters? So in our engineering drawings, we need to specify the exact size that we want and what we're happy with, because sometimes we're happy with plus or minus 2 millimeters. Sometimes we might need plus or minus 0.001 of a millimeter. So our engineering drawing is our chance to specify what that size will be. So we need to specify both the maximum and the minimum allowable size. So we have the maximum here and minimum size. So we can say, here's our 10 millimeter. We can say, well, we're happy if we go to this size. We're happy if we go down to this size. And it's generally much cheaper to produce items with a generous tolerance. So we don't want to be specify over exact tolerances. Essentially with tolerancing, we're saying if we're outside of that tolerance, that part is not suitable for our application. It must be reworked or scrapped. So in here, a tolerance. So the actual word tolerance, what is a tolerance? Tolerance is the difference between the allowable maximum and minimum size. So it's the amount of variation there is. So, and for one thing, we've got the golden rule of tolerancing, and that is to always specify as large as possible a tolerance without sacrificing your quality. So that's the golden rule of tolerancing. So, displaying tolerances. So we can have, in SolidWorks, we can have the basic size of a component. We can then add a bilateral tolerance. So you can see bi means two. So you've got two tolerances, two sizes. So here we are, we've got our basic plus our bilateral. So we can go two amounts in two directions. A bilateral can also be in symmetric. So there's a term plus or minus 0.15. So it's plus 0.15 minus 0.15. So it's still bilateral. We can show a bilateral tolerance by the values. So instead of saying plus so much minus so much, we can actually put the sizes here. This method here is really good. It doesn't rely on somebody to actually do the calculation. What is 0.15 minus 50? Some people need a calculator to do that. Some people will get it wrong. So you can be more precise by putting it together. Now unilateral, uni is one. Just think of a unicycle, has one wheel. So a unilateral tolerance goes in one direction. So you can see we have a basic size of 50, and in here we have 0. And so it's exactly 50, but it's allowed to go up to 0.3 larger. We can go 0.3 lower. We can do a unilateral tolerance by using the number 50 and the amount that it goes down. So that's a unilateral tolerance. So that's the part to know about these tolerances. Now what I'll do is actually show how we place those in SolidWorks and how we can use those. So I'll just open up SolidWorks. So here I am in SolidWorks. I've got a drawing sheet, and I've got just a square drawn here with some dimensions on it. So I've put the dimensions here. I can double click. Maybe I'll make that 450. So I'll accept that. There's 450 dimension. Now to add a tolerance, I go to the side here. Tolerance, what do I want? I want to have a bilateral tolerance. So I can choose here. I can put in plus or minus plus 0.1 minus 0.2. and accept that. And there we are, 450 plus 0.1 minus 0.2. So that was, I click on the dimension, brings up the box, says tolerance and precision here. So it's bilateral. We talked about symmetric. I can have plus or minus 0.2 of a millimeter. We'll make that plus or minus 0.2. So you can see here in SolidWorks, click on the dimension, we can add the tolerances to our drawing for a specific size. So that's 450 plus or minus 0.2, maybe the 500, I want to make that plus or minus, 500. Tolerance will bring up a symmetric tolerance, and it's plus or minus 2 millimeters in that direction. So that's how we can set tolerances in SolidWorks. Now I'll go back to the presentation. So that was looking at tolerances. So here, here's a little activity for you. So here we are. Here's a dimension we see on the drawing, 12 plus or minus 0.5. What is the type of tolerance? And what is the size of the tolerance? You can check your answers in the formative quiz. So, tolerances. We don't need, even though all dimensions have a tolerance, we must put that and create, all dimensions must be given a tolerance. But we don't need to label them on each individual dimension. Some of the things that we can do in our drawing, we can put a general note on the drawing. All tolerances except otherwise stated is plus or minus 0.1, or it is plus or minus 1. So that is a very common way of doing it, to put a general note on the drawing, maybe general tolerance is plus or minus 1, and then it is wherever you put the exception, that is what the tolerance will be. Some drawings can have this note, like here, where it says tolerances except where otherwise dimensioned are in these range. So we can have a size range up to 75 millimeters. They're this range, between this range, they're here. We can change the tolerance. Also, angles have a tolerance as well. Another one for castings might have a percentage. Say, well, percentage of the casting thickness is the tolerance. And a very common way is to use decimal places. So if we have a number 5, it says, well, that's 5 plus or minus 0.5. If we write it as 5.0, it is plus or minus 0.05. And same for if we use double zero. So we can use a number of decimal places, but these are shown on the drawing sheet or added to the drawing sheet for these tolerance specifications. They're not assumed, they must be specified on your sheet. And your drawing sheet is really a contract, legal contract to say this is what I want. So if there's no reference to it on the drawing sheet, you cannot expect anything, people to understand or guess what you want for your tolerances. So here's some terms. People will often see these terms: a fine tolerance, a medium tolerance, coarse or very coarse tolerance. So the Australian standards, AS 1100, actually specifies what people mean. So a fine tolerance means something for small sizes, and it means there's small size over here. It means something different for large sizes over here. So there really is a value if someone says, I want a coarse tolerance, that these values are actually specified in the Australian standards and these terms. And you can see F for fine, M for medium, C for coarse, V for very coarse. The people can use that as well. So they can use those words for their tolerances. As I mentioned, angles also have a tolerance. So we have a linear tolerance, angular tolerance. So we can, again, put them in a range, upper and medium size. We can use bilateral, we can use symmetric, and we can have unilateral, where one of the values is 0. So we can have all of those different ranges of specifying what the angle is as well. And we must do that. So the drawing must say linear size are within so many millimeters as a general tolerance, but we also must do the angle tolerance as well. And they're generally shown in the drawing template. So I'll just go to SOLIDWORKS to show you that. So here we are back on the SOLIDWORKS drawing sheet. Now that's the same one that I had before. This is just the standard template. So if I zoom in here, it says, unless otherwise specified, dimensions are in millimeters. Tolerances, so we should be putting in here linear, maybe plus or minus 1, angular might be plus or minus half a degree. So we must fill in those bits of information in our title block of our drawing sheet. So you might not have seen that there before, but that's a very important part for the drawing sheet. So we've talked about tolerances of individual parts, but we must also think about tolerances of how we fit together and tolerance accumulation. So that's where we put multiple sizes and tolerances add up. So one of the things, you must have a lot of care and ensure that tolerance accumulation is controlled. So if we have one part sitting next to another part, sitting next to another part, as those tolerances add up, so if you're putting those parts together, the variation can lead to lots of issues, and it has, in many manufacturing situations, caused many problems, many hours of trying to solve what went wrong here, and it is an accumulation of tolerances. So tolerance accumulation, just want to go through some of this to show you about tolerance accumulation. There will be some formative and assessed quiz questions on them as well. So we can have external tolerances. So we're measuring these components. So you can see item B is here, has a dimension B to here, which fits with item C over here, which fits with item D. So you can see that dimension D talks to the size D, C is size C, B is size B. A is the overall size. So what we're interested in is what is the variation in A, given that B has tolerances, C has tolerances, and D has tolerances. What are those total tolerances? So for A, it's actually the sum of the individual tolerances. So, okay, so here's an assembly made up of components B, C, and D. And the size ranges are shown here. Your task is to tell me what is the largest and smallest size of that total width. So what's going to be the largest size that total dimension can be, and what is going to be the smallest size? And then the question is, what is the tolerance of this assembly? You can check your answers in the formative quiz. So we talked about external tolerances. Now there can also be internal tolerancing as well. So we can have internal tolerance accumulation. So here we've got item D. So we can see here's item D that comes around here. And it has a size. So we've made D with a range of tolerant sizes. So it can be upper size and lower size for D. Now we need items B and C as a pair to be able to fit within D, say, or to have a type of fit. So B has its own size and range and tolerances, and C has its size and tolerances. So the question is, what is the type of fit going to be? If B and C might be smaller and have a clearance, it might be tighter and have an interference fit. And some applications we want that interference fit to hold it together. Other times we want to have a clearance there. So that's the next topic, is internal tolerances. So here is the way to look at it. So we can look at size D, so we can look at a chain. So D is equal to the sum of B plus C plus the clearance. So overall you can draw it as a chain. So I can say if we start here, D equals B plus C plus clearance. So we can write a chain, and then we can do the sum of it. So we create a chain to solve it. Step 2 is rearrange it. So we can rearrange that equation, D equals B plus C plus clearance. We can rearrange that in terms of clearance. So we can have clearance is equal to D minus B minus C. So we can find then what is the maximum clearance and what is the minimum clearance. So we can get the maximum clearance. It's going to be maximum clearance. You can look at the clearance is this value. That's going to be maximum when D is maximum, when B is minimum, and where C is minimum. So we rearrange, form a chain, rearrange it, and then we can solve it for the condition that we're interested in. So here's an example. Here's some values. Now find the upper and the lower sizes, limits of the clearance for this section. You can check your answers in the formative quiz. Here's another set. So we can check here to see what type of fit this is. So check your answers in the formative quiz. Now here's a much more difficult problem, but I like to let students try for themselves and try and solve this. So here's two items that push together. So it's a dog clutch. You can see here is the clearance. So these don't, there's going to be a clearance there. So the question is, what is the range of that clearance? So these two items fit together and they will contact on that face. So you can see when they contact together, we need to calculate what is the clearance. So there's dimensions here for the parts, and we need to solve that as to what that size is when they're pushed together. And there is enough information there to solve it. It's a difficult question, but it's one just as an extension question for you. So thank you for listening to this presentation.